here. Is the father of your mother the same as the mother of your father? And number 2, is the sum of the squares of 4 and 5 the same as the square of the sum of 4 and 5? Show your work. So if I were to go personal, the father of my mother, his name is James. But the mother of my father, her name is Linnea, which is a really cool name because if you take that away and then move it over to there, you get linear, and that's just beautiful. So besides being a nice name, anyways. All right, so there we go. Here's a single counterexample of it. Because we're going through a different direction. We're going here through the line of my mother. Here we're going through the line of my father. And we are talking about different genders as well. Next up, is the sum of the squares of 4 and 5 the same as the square of the sum of 4 and 5? So here we see that if we reverse things here, if we add the squares together in a sense like a Pythagorean theorem, that's what Pythagorean theorem does, here we get 41. And if we sum them first, then square it, we get 81. And clearly they are not equal. So today we're going to be looking at something called a composite function. So, we are going to be making a composite function. Take a moment to follow these instructions. So you're going to write down the day and the month of your birth just right here. I don't care if it's in comma or separated or as a single number. Then you're just going to follow those instructions and see what you get. So I'll do the example here of my own. So I'm going to write down 20 and 9. I don't know if I'm going to write it as a date or a comma or whatever. So I take the 20, I'm going to double it, and I'm going to multiply by 10. Then I'm going to add 73, 2,365. Now I'm going to add September to it, 2374. And now I'm going to subtract 365. Oh, and look what I get, 2009. And the original date there, the original number I got was 29 or 2009. Like that. So, what do I notice, of course, about my final answer is that my final answer is what my original number was, effectively. So why will this always work? Is this magic of sorts?
73. That's why I was wondering what the 73 is, but I think I know now.
Well, let's call D day.
73 times 5 is 30.
And let's call M month. Month M. So what do? I'm going to double my day, so 2 times day. Then I'm going to multiply this by 10, so all of this is going to multiply by 10. Then I'm going to add 73, so all of this adds 73. Now I am going to multiply by 5, so everything here has to multiply by 5. Then I'm going to add the month in just a minute. So after all this, I have to add my month. And I am going to subtract 365 from this. So this is what the math looks like. And what this does is that they are embedding confusion. When they embed confusion, you get mystified. Wow, look. I've done all this and I'm mystified. But really, what is it that we're doing? Well, let's multiply this stuff out. So here, that multiplies out to be 20D plus 73. Now when I use the distributive property, I get 100D plus 365. Bring down the plus M, bring down the minus 365. Bring down the M, the minus 365. What do you notice about the 365s? They drop out. So would it be so magical if they said, take your D, multiply by 100, and add M? Well, what does multiplying by 100 do to any number? Any number, what's it do? So if I were to, all 100 does is take a digit or a number and shift it over 2 places. So from the ones place to the hundreds place instead. And then effectively all we're doing is adding M to that. So it seems magical, and I hate to ruin the wonder. Each step can be called a function. So each step, that is, I add 73 and I multiply by 2, etc. But if we put it all together as a single function, we end up getting the same result as following it step by step. So we can call, this is called the composite function. So notice, like I said before, multiplying by 100 and then simply adding the month is equivalent to following all those steps up there. So instead of doing 4 or 5 individual steps, we can just do one step. Of course, we lose the magic in that, but for this specific case. But that's exactly what's called a composite function is, essentially. It's a function within a function, and sometimes even deeper, within a function within a function. We can go infinitum. Okay, so suppose f and g are functions. The composite of g with f, written as and there's a little bit of a circle. So that's the problem here, is it's not an O, so don't make it big, but it's also not multiplication. So multiplication, we put a dot. This one's an open dot, an open point, as opposed to an O, which is a little bit larger. So the problem, of course, is context. Yes, it might look like you're writing goff or fog or whichever way you write it, because we are going to switch them. But we read it more like this. We write it the composite of G with F. Or the other way around, if we write it the other way around. If we say F with G. So we can write it in this manner with parentheses around the composite part. Or this is the embedded way. The embedded way. F of X is inside, and then G of that is happening. So G of F of X, G of F of X, or we can read this, the composite of G with F. Composite of G with F, or G of F of X. Gets complicated. Now here's the most favorite sentence in the history of this class you will ever know. The domain of the domain of the composite of G with F is the set of values of X in the domain of X, for which F of X is in the domain of G. Oh, that's beautiful. Hashtag what? So on page 2, here effectively is what a composite function is. So think of this as an assembly line where we pass a result of one of the functions into the other function, depending on order, so it's important. So let f and g be defined by f of x is 2x squared plus 3x, and g of x is x minus 7. So we're going to evaluate this. So the composite of f with g evaluated at negative 2. So what ultimately do we do? Remember that this means, another way to write it, is to embed, like so. So the first thing we're going to actually want to do is evaluate g of negative 2. So let's find out what g of negative 2 is, and we're going to pass the result on to f. So g of negative 2 is simply this, negative 2 minus 7. All I did was put a negative 2 there, and clearly we see we get a negative 9. So what do we do with that? I'm now going to pass the negative 9 on to the f of x. So now f of x is going to be evaluated at negative 9. So we're farther away from the negative 2, but that's okay. And now we're going to evaluate. So 2 times negative 9 squared plus 3 times negative 9. Remember, when we multiply here, we have to exponent first. So 2 times 81 minus 27. And you can finish these 2 steps up as 135. So let me remember to always bring the answer back together. So f, the composite of f with g of -2 is equal to 135. Remember to box or circle your answers just to make it a little bit faster. Bring it all together. So, simply put, we evaluate a function at one particular point and we pass that on to the next function. So here we evaluated g and passed it on to f. What's this one saying? Well, this one's saying is that I'm going to evaluate f first and then pass that result on to g. So my first thing to do is actually evaluate f of -2. So I'm going to substitute the -2 into f. And we can do all of this essentially at once. This is 4, 2 is 8, minus 6. So the result is +2. So let's pass that on to g. So g of +2 now. Notice there is no rule to say just say take the opposite. Don't just say, oh, take the opposite, put it in. That's not necessarily the case. In this particular number, I get opposite here. That will not necessarily be the case. So I substitute in a 2 there, and our ultimate result is -5. So that means the composite of g with f at -2 is -5. Each function does its job and passes it on to the other function. When we substitute in, and by the way, there's a dozen different ways to read this, so this is a problem. You're going to, like, just these, 3 little variables or function names and a number and then parentheses, etc., can be read a bunch of different ways. So generally, I'll be saying, like, f with g of 4, but you could say f of g of 4, or you can say the composite of g with f of 4, and you can even say f of 4 followed by g, like going in the other way. So it gets kind of complicated. But when we do evaluate this first one, we do get 1 over 69. We evaluate the second one, we get 1 over 49. So what's our conclusion now? So let's back up a little bit and go here to conclusion. More specifically, we know that 3 plus 4 is equal to 4 plus 3. What's that property called? So this here is called the commutative, as in to commute a sentence or to commute to work. Commute means to go back and forth, right? Or to go back on, I guess, if you're commuting a sentence. So what's our conclusion about composites and commutating, whatever the verb is there? No commuting composites. Which we already know that commutative property doesn't always work. 3 minus 2 is not the same as 2 minus 3. So the commutative property is a very distinct and limited. It hardly works. In fact, it works far less than you think. With addition and multiplication, yes, but not with other things. And like we said earlier, the father of my mother is not the mother of my father. Does the commutative property work there with family trees? It does not. Okay, so we want to remember that we have to evaluate each individually. A second way to evaluate something is not simply to evaluate then pass the result, but it's actually to find what's the super mother function, what's the one function that this is actually describing, and then just evaluate that new function. So this is where composite functions get really fun. So we're going to derive a single formula for the composite of f with g of x. So what does this one mean? Again, it means I take g of x and I embed it inside of f. So I take g of x and I'm going to embed it into f of x. So f of x is equal, actually let me unpack that, say it better. F of g of x. Remember we can use the little composite circle as an operation or write it like embedded form here. So it's 2 times x minus 7. Don't forget we're going to square that. Plus 3 times x minus 7. Do a few steps at once here. Remember FOIL, we can do x squared minus 14x plus 49 plus 3x minus 21. And when we simplify all that at once, we get 2x squared minus 25x plus 77. So either I evaluate one function and then pass the result to the other, or I just evaluate the composite. This won't always work, but it does work probably most of the time in the 90 percentile. So this is my composite function. I can simply do it once there. So what about the other one? So this time I'm going to take f of x and I'm going to embed that into g of x. So this whole function is now going to be substituted over there. So all we simply say is 2x squared plus 3x gets substituted into the g of x. So we just say the function minus 7. The function minus 7. So this one, less work to do. 2x squared plus 3x minus 7. And that is my composite function of g with f as opposed to f with g up there. We can verify that these two composites are not the same because when we graph them, we should get different results. So if I were to graph these, notice that the second one graphs as so, and the first one graphs as so, and clearly they look similar, but obviously they're not the same because they're not one atop the other. So we see that they are not the same. All right, your turn on practice 2. I would like you to derive the composite of f with g of x, and then do the same thing for g with f of x. So the first one here simply says, take the fraction and square it. So take the fraction and square it. And we don't need that parenthesis there. Square. Now, the property of exponents, that when I have a fraction here, I'm going to essentially send the exponent to both of these. So 1 squared is 1, so that's simplified. I don't need to write anything more. And if I did FOIL this out, it gets way more complicated. So I'm going to argue to keep it simple. Don't bother multiplying out the binomials, etc., unless you need to add something else to it. All right, so here is a complicated part. So I'll read this and follow along, and then we'll try to unpack what that means. The domain of G, the composite of G with G with F, is the set of values of X in the domain of F, for which F of X is in the domain of G. So, yes. Let us consider what this means. So, we have to consider what the domain is here and the domain is here. And kind of bring a hybrid of the two when we're deciding what the domain of the whole thing is. So, first we're going to find the domain of G with F, then we're going to find the domain of F with G. But the first thing we need to do is find the domain of each one. So, I'm going to find the domain of G. This is my personal notation, like this. I don't know if other books or stuff do that. They probably write it out all the way like this. So I'll just speed it up like this. Okay, so let's just look at the function g right here. And we look here and we see, well, what restrictions do we have? Well, we have a fraction, our variable's in the denominator. So that means the only thing we can't have downstairs is a 0. So what's the only value of m that makes the denominator 0? Well, the answer there is 3, so m cannot be 3. Now to find the domain of f, we just look here and we see, well, what values of m make f into an illegal function? Well, we can't take square roots with real numbers. We can't take square roots of negatives. So that means m can be 0, but it has to be 0 or greater. So if we wanted to find out what the domain of g with f is, first I'm going to find out what that function is. So I'm using m as my independent variable. So remember, in this case, I'm going to take f and embed it inside of g. So here's f, and I'm going to embed that inside of g. So I say 2 over the square root of m minus 3. So there are two types of domain issues we have to consider. Number one, we have a domain restriction right here of f of x, or f of m. So this is already a given as a domain restriction, because right here we can't go into the negatives. But we also have another restriction right here. What else can't we do?
No.
So this is already part of the domain. So if I were to consider the domain of g with f, we already know that one of my restrictions is I have to be greater than or equal to 0. But there is more to it than that. Down here cannot equal 0. More specifically, the function right here, that is the function f of m, cannot be 3. It can't be 3. So notice what I can do here. It sort of sounds complicated, but if I take this function and substitute it into the domain of the other one, then we get this. The square root of m cannot be 3. And if we look here, the square root of m cannot be 3, because if all of this is 3, we get a 0. So if I take the square of both sides right there, m cannot be 9. So there's my other restriction. I have two restrictions for this composite function. The first one is just the embedded function. The embedded function itself, we have that domain. But then we have to consider anything else that's in this domain right here that might mess up this whole thing. So it's this domain plus any other additional ones that might mess up the whole composite function. So let's walk through it going the other way. So what is f with g of m? Well, in this case, I'm now going to take this fraction and embed it into there. So now we say the square root of 2 over m minus 3. So notice when I'm considering the domain of this guy right here, I already have one restriction down here, and that's the beginning restriction here. M cannot be 3. M cannot be 3 because inside would make this a 0 in the denominator. So we already have one restriction. The one restriction is the actual domain of the embedded function. So now we have to look at this whole thing and see what are restrictions, what make this right here equal to a negative number, because I can't take a square root of a negative. So again, what did I do up here? I took the function and substituted in the domain of the other. So I took f and put it here as the domain of g. Well, let me repeat that, but let's do g. Take the function g and substitute it right here into this domain and solve this equation. So what's that? That would be 2 over m minus 3 cannot be greater than or equal to 0. It has to be greater than or equal to 0. Now this one is actually not very solvable easily. Why? Because what if I multiply this by m minus 3 on this side and over on this side? What happens to my variable? Well, no variable, what's 0 times anything? It disappears. And if my variable disappears, I can't actually solve it, at least algebraically. So this one, instead of solving algebraically, I just think about it. So what values right here, notice it has to be positive. So what values of m are going to make this positive right here? What values of m are going to make this positive? So let's think. Well, if m were 3, we already can't do that. So if m were 4, this whole thing would be positive. It would be a fraction. If m were 5, the whole thing would be a fraction. So let's go under that. What if m were 2? Well, that would mean this would be a negative 1, so this whole thing would be negative, which means this negative would be inside. So what restrictions do I have? Is in this case, m cannot be 3, and more specifically, m has to be greater than or equal to 3. Wait, why greater than or equal to 3? Again, because anything less than 3 would make this negative.
No, greater than or equal to 4.
Oh, good. So
it would be 0.
Exactly. So here's the problem. If I say, so to solve this part right here, so that's to make it negative. So let me just clean that up and delete that part. So m has to be greater than 3. So, but notice this. If m has to be greater than 3, what's that do about my original domain that I put in there? I don't need that. So see how there's not like step 1, step 2, and do it? We do have to find the domain of each individual function, and then we look at the whole composite on its own, and then we just have to kind of play with it to see what works and doesn't work. So in the end, my domain here for f with g is that m has to be greater than 3. So after all that, just straightforward like that. All right, the last thing that we're going to look at is transformations and their applications. I repeat, because transformations are functions, you stretch, vertical compression, or shifting left or right, they can also be composed, but remember that they aren't commutative. So what we're going to look at is, here is one scale right here. So S stands for scale, or a stretch or something of that matter. So notice what happens here, that we're doing a horizontal stretch by 2. And this translation is I'm going to shift right 4 and down 3. So we can actually describe that in words, exactly what I just said there. So S means that we are going to do a horizontal stretch by factor of 2. You do not need to mention y, because by default nothing happens to y. If you wanted to say no vertical stretch or no vertical compression, that's fine, just unnecessary. So the translation, what happens here, this part here tells me that I'm going to shift or slide right 4. And this part here says I am going to shift down 3. I just use the verb once. I don't need to say it more. So remember what this right here says. If I'm saying the composite of t with s of x and y, what does that mean? One is embedded inside the other. So s is the one that gets embedded. So I take this, what happens here, and I'm going to embed it into the x and the y over here. Now again, y goes to y, so it doesn't change this right here. But the 2x is going to replace this one. So what's that look like? So I'm going to take the 2x and I'm going to substitute it into there. So now I say 2x plus 4, and the y gets substituted over to there, so y minus 3. the first thing that happens here, according to order of operations, is I'm going to multiply first. So that means the first thing that happens is horizontal stretch by 2. Then I'm going to shift right 4 and down 3. So note that how that's going to be slightly different than the next one. Now I'm saying S with T. So now I'm going to embed the x plus 4 into this expression, and I'm going to embed the x minus 3 into this. So to say this, S with T of xy is equal to, now I'm going to embed the x plus 4 into there, and the y minus 3 goes in as well. Again, not much is happening there. There's no vertical stretch, so that's not being affected much. So notice when I do the distribution here, I get this, 2x plus 8, y minus 3. So in words, what would happen here? Order of operations says, I am going to do a horizontal stretch by 2, but now I'm going to shift 8. Now I shift 8 right, down 3. So notice it's not the same. Like we said, the commutative property doesn't work if I embed one inside the other. Because if I embed like I did down here, notice that the shifting is also being stretched. What? The shifting here is also being stretched. So that's why it's important for us to follow through here. So a horizontal stretch by 2. Forgot an S in there or C in there. My word. And then we're going to shift right 8 and down 3. Remember to complete your notes, 1 or 2 sentences to summarize, and also provide questions on the side there.